Okay, welcome back to Virtual Science. Today we're going to continue our exploration of chemical bonding. In the last part of this unit that we've been working on, we've been focusing on ionic bonding, which is when the atoms gain or lose electrons, the metals become positive ions because they lose electrons, and the nonmetals gain electrons to fill up the outer energy level, and then they become negative ions. There's another way for the nonmetals to fill up those outer energy levels, and that's by sharing a few electrons, up to 3, with other nonmetals. And that sharing of electrons is called covalent bonding. Okay, and as I've mentioned before, the prefix co means to share. And what are they sharing? The valence electrons, and that's where the valent comes from. So they've called covalent compounds, and it's the result of sharing electrons. Covalent molecules form between a nonmetal and another nonmetal. Unlike ionic compounds that were just called ionic compounds, covalently bonded compounds are called molecules. Okay, now, I said that on the periodic table, covalent compounds are between a nonmetal and another nonmetal. So it's these elements over here that I kind of have highlighted. So it would be carbon, and then family 3, family 2, family 5, family 6, and family 7, where we have oxidations number -3, 2, and 1. So family 7 needs to share 1 electron with somebody, and then 7 plus the 1 is sharing would be 8. Family 6 needs to share 2 electrons. 6 electrons that it has plus 2 that it would be sharing is 8. And family 5 has 5 valence electrons. If it can share 3 with somebody else, then it'll have 8. And then family 4 needs to share 4 altogether, but it only does it up to 3 at a time. So we're going to see how that works. Okay, so covalently bonded compounds are called molecules. Okay, they can form single, double, or triple bonds, depending, like I just said, whether they share 1, 2, or 3 pairs of electrons. So in one pair of electrons, there's 2 electrons, 1 from each atom. If they're sharing 2 pairs, there's actually 4 electrons, 2 from each atom. And then 3 pairs, would be a total of 6 electrons, 3 from one atom, 3 from the other atom. So they both share 3. Nonpolar molecules. When the sharing happens, it doesn't always happen equally. Sometimes there's equal sharing and the molecules are nonpolar. That's because the electrons that they're sharing are spending equal time with both of the atoms, and so they end up being nonpolar. Now, if the sharing is unequal, then that means kind of the big one sort of bullies the little one, is what you can think about it. And so they both want to share this electron, and the big one says, yeah, well, that's cool, because I'm way bigger than you are, so I'm keeping the electron most of the time. So poles means it has a positive end or a negative end. So if it's not polar or nonpolar, it does not have a positive and a negative end. So you can think of it like a magnet. A magnet has poles. It has a positive end and a negative end. If this negative end was the electron and it was bouncing around, okay, it would be shared unequally by the dark side. So the dark side would be keeping the negative electron most of the time, and it would become polar. If it's nonpolar, it would be traveling and spending equal time everywhere. Like this piece of wood is nonpolar because it does not have poles. Now, diatomic molecules are just like what their name says. Di means, the prefix means two what? Atoms. Diatomic. Just like when we polyatomic, poly meant many atoms. This means 2 atoms, diatomic. Diatomic molecules are covalently compounds with 2 atoms of the same element. And examples of those would be like O2, which is the oxygen we breathe, N2, which is the way nitrogen is in the atmosphere, and the atmosphere is mostly nitrogen, Notice that all of these are two atoms that are identical, two oxygens, two nitrogens, two hydrogens bonded together, and two chlorines bonded together. And since the atoms are identical, okay, they both want to share the electrons, and they're both the same size, so they share them equally. Nobody can kind of dominate the situation. So diatomic molecules are always nonpolar because the electrons are shared equally. Now, some molecules like CO2, well, carbon is a much smaller atom than oxygen is. So there's not going to be equal sharing between the carbon and the oxygen. But they end up being nonpolar anyway. And then I put in the notes because the opposite charges of the nonpolar bonds cancel each other out. What in heaven's name is that supposed to mean? Well, I put a little diagram down here. So the oxygen is a larger atom than the carbon. So between the first oxygen and the carbon, there's unequal sharing, and the oxygen keeps the electron most of the time. So that becomes slightly negative. But the same thing happens on the other side of the carbon. The other oxygen is not sharing equally with the carbon, and so it keeps the electron most of the time. So both ends of the CO2 become slightly negative. And so that's what it says here. That's what it means when it says because the opposite charges of the nonpolar bonds cancel each other out. The opposite charges of the two oxygen ends cancel each other out, the two negative ends. Now, if the molecule has one end that's slightly positive and one end that's slightly negative, it's polar. Okay, so just like I explained, anything that has poles, a positive end and a negative end, okay, is polar. Okay, so it says one molecule has an end that's slightly negative, and one end has an end that's slightly positive. Overall, the molecule is neutral. Like I just explained, kind of the big one sort of does not share equally, or sort of, picks on the little one and is like, okay, well, we both want to share this, but I'm bigger than you, so I get what I want, and I'm going to keep these electrons that we both want most of the time. So I put in notes, the electrons are shared in a molecule are held more closely to the atoms with the larger nucleus. Okay, they both want the electron, but the big one gets its way. Now, water is the most important polar compound there is. In the 6th grade, you learned that water was a polar molecule, and probably then get as much of an explanation. Hydrogen is small. It's the smallest element on the periodic table. It has an atomic number of 1. And oxygen has an atomic number of 8. So it's much larger than the hydrogen. So the oxygen nucleus is larger. Okay? The oxygen will hold the electrons more closely, the ones that they want to share, and that unequal sharing results in a polar molecule. Now down here I put a diagram of a water molecule. These two ends are the hydrogen. The big atom is the oxygen, and it has 6 valence electrons and an oxidation number of 2 negative. That means it needs 2 electrons to fill up that outer energy level. The hydrogens have an oxidation number of 1, so they need 1 electron to share with the oxygen, and this one needs 1. So if they need 1 and they share 2, the oxygen shares 1 with each of these 2, and these 2, everybody in these end up with a full energy level of 2, and the oxygen ends up with a full energy level of 8, because each hydrogen is going to share an electron with the oxygen. So 6 plus the 1 it's sharing with the hydrogen is 7, plus the 1 it's sharing with the other hydrogen is 8. So by sharing these electrons, the oxygen is like, cool, I got my full energy level of 8. Okay. However, the oxygen is larger than the hydrogen. It keeps the electrons most of the time. Okay, 2 extra electrons make the oxygen negative, and it becomes polar because it's not equal sharing. These electrons aren't going back and forth and spending an equal amount of time between the oxygen and the hydrogen. They're spending most of their time over here with the, the big atom that's like, okay, well, you want them, but I got them. Okay. The electrons are not shared equally. The unequally sharing results in a polar molecule. Okay, so the hydrogen ends up slightly positive, oxygen ends up slightly negative, and every water molecule has a positive end that's attracted to a negative end, and they clump together. Now we're going to look at this video clip from this astronaut in outer space, and he's going to wet a washcloth. And if you watch, you can see, you can imagine how the water all clumps together and it almost looks like jello, because the positive end of one is attracted to the negative end of the other one. And then the next one's positive end is attracted to that one's negative end, and so on and so forth. And they all stick together because it's like magnets, positive ends sticking to negative ends, and they all stick together. So it looks like it's all clumped up. Okay, here's this video of the astronaut in outer space.
The question is, if you get a cloth dripping wet without gravity and you wring it out, what's going to happen? What will happen to a wrung out cloth? So, and I had to use equipment that was here on board the space station. We may have the coolest washcloths ever here on the space station. I'm going to show you. Here's one of our washcloths. And it's compacted. It's put down into this little tiny hockey puck so that it saves space. But when you open up a hockey puck,
The microphone's floating.
And you pull out your washcloth, this is the one I'm going to use for the experiment today. And so when you open up your hockey puck and turn it into a washcloth, it was compressed in a great big vise somewhere. Okay, so here's my washcloth, like a magic trick. And now I'm going to get this soaking wet, and then we're going to see what will happen when we wring it out. Meredith and Kendra suggested that I dip this in a bag, but bags don't hold water in space, so instead I filled a water bag. This has drinking water in it. And I'm going to squirt a bunch of water into this washcloth.
That's how it clumps up. It's because of that attraction.
Okay, so here's a soaking wet washcloth. Get the microphone so you can hear me while I'm talking. And now let's start wringing it out. It's really wet.
See how the water pulls together the positive ends from the negative ends.
It's becoming a tube of water. The water's all over my hands. In fact, it wrings out of the cloth into my hands. And if I let go of the cloth carefully, the water sort of has it stick to my hand. Okay, so the experiment worked beautifully. And the answer to the question is the water squeezes out of the cloth, and then because of the surface tension of the water, it actually runs along the surface of the cloth and then up into my hand, almost like you had Jello on your hands or gel on your hand, and it'll just stay there. Wonderful moisturizer on my hands. And the cloth doesn't really unravel itself. It just stays there floating like a dog's chew toy, soaking wet. Great experiment, worked perfectly. Meredith and Kendra, congratulations, great idea.
Okay, so on the video, you should have seen how the water molecules all pulled together, and that's why it looked like gel. The astronaut said surface tension. Surface tension is another word for that polar attraction of the one molecule to the next molecule. It creates tension on the surface. Sometimes people use that word, but it's really what we were looking for is that positive end of one water molecule being attracted to the next so that they all clump together and they look like that goo. Now, I want you to answer these questions independently, and we'll pick up here next time. I hope you're having a great day, and we'll see you soon.